Okay, all right. Thanks everyone for attending this seminar. Today, Lauren and I will talk about some statistics and coding. Next slide, please.
Sorry.
It's okay. So here's the agenda for today. First, we're going to talk about some basic concepts in stats, like p-value, confidence interval, and we'll also talk about how to set up tables for clinical research. Next, please. Okay, so can you guys let me know how many of you have heard p-values before? You can give me a thumbs up or something, or like emoji. Okay. Okay, cool. Quite a few. Nice. So I won't read a formal definition. It's just not that intuitive. But as you can see, the bell-shaped curve on the right hand, if you think about your data, it's like if it's like normally distributed, like most likely observations are in the middle, like very unlikely observations are at the two tails. A p-value, which is a shaded gray area, is a probability of unobserved or more extreme results arising by chance. So you want your p-value as small as possible. Like hopefully that means the less likely arising by chance. Next slide, please. Okay, so in the medical literature, a two-side p-value less than 0.05 is usually considered significant. For example, this paper we just extracted from the literature, and you can see they have a p-value of 0.005, which is less than 0.05. So the authors concluded there is a significant reduction in BMI percentile. We'll talk about like the research methods, the linear regression in later slides, but I just want to give you guys idea how to report the p-value in medical literature. Next slide, please. Okay, how many of you have heard confidence interval before? Okay, cool. So confidence interval, we usually use 95%. It means if the study was replicated many times, the true incidence will be contained in the computed interval 95 of the time, assuming there's no confounding bias. It just gives you a range about the true value. And there are different ways to calculate confidence interval based on your study population. I just list two equations here. I won't go into details, but just give you an idea, confidence interval can be calculated. Next slide, please. Okay, we have an example for today. Let's say our research question is how does lifestyle impact blood pressure after accounting for demographic characteristics? So if you look at this research questions, what variables you think we should take a look in the data? So lifestyle for sure, right? That's our exposure. And blood pressure is our outcome. And demographics such as age, sex will be covariates. So for the lifestyle, it's either active or sedentary in this research question. For blood pressure, it's either continuous or binary. Continuous just as it is, but binary we can use cutoffs to make two levels of blood pressure, high versus normal. And also for demographic characteristics, age is continuous, sex is male or female, it's binary. Okay, next slide, please. Okay, so in medical research or clinical research, the table one is usually or always descriptive statistics. It just describe the sample demographics. For example, we just report average age of the sample, the proportion of men and women in the sample, the breakdown of race, what's their annual income, their education level, etc. So if you have a categorical variable, you want to report the n with percentage, just quantifies how much the outcome exposure are occurring in the population. And if you have a continuous variable, you just calculate a mean with standard deviation. Next, please. Okay, once you have your variables figured out, next step will be coding those variables. The reason we need to recode the variable because different regression models takes different types of variables. For example, there's a regression model called logistical regression. It calculates odds ratio. We will cover this later, but I just want you guys to know if you are doing a logistical regression, the outcome must be coded as 0 or 1. It has to be a binary variable. For example, our outcome is blood pressure. You will use a 120 as a cutoff. If it's less than 120, and then we code it as 0, that means normal blood pressure. If it's greater or equal to 120, we code it as 1. It means high blood pressure group. And 0 is a reference group, and 1 is a outcome, is a category we're interested in. On the other hand, linear regression model, the outcome must be continuous. So the blood pressure stay as it is. For demographic variables, you can leave left as it is or collapsed based on the sample size of each category. For example, sex, we usually just do male and female. Age is continuous, so just keep it. But for race, since there are many categories, due to the power issue, we usually collapse into 5 categories like non-Hispanic white, non-Hispanic black, Hispanic mixed race, and other. Sometimes mixed race and other can be combined too based on your sample size. So the rule of thumb is if it's less than 10% of the each category, we typically collapse just to increase statistical power. Next. Okay.
So there are a lot of options of statistical packages that you can use to analyze your data. At UT Health, we use mostly Stata and SAS. R and Python we're exposed to a lot in like data science classes, but mainly Stata and SAS. And then there are other packages available too, or softwares available like SPSS, MATLAB, etc. So if you haven't been exposed to any of these before, it would be great to just, pick one, get familiarized with it. I think that it's easier to learn a new software once I've already had learned my first software. So just pick one and get started, and you'll pick up on it. But today, specifically, we're going to talk about Stata and SAS. And for descriptive statistics and Stata, there on the left side here on this table, it says continuous variables, and on the right side, it's categorical variables. But in order to get the mean and standard deviation of a variable in Stata, you use the sum command. It's short for summarize. And then you put the variable name that you want to get. And I'm not sure if you can see my mouse, but like if you just did sum and age without this comma detail, you would get this mean and standard deviation. But there's the option to also include the sum, age, comma, detail to be able to get all of these percentiles, the variance, skewness, and kurtosis if you're looking, at normality and other things, just to get a little bit more information on that continuous variable. If you're looking at categorical variables, we use the tab command, short for tabulate, and just insert the variable name that you're looking at. So here we're looking at sex, tab sex, and we can see that we get the frequencies and the percentages, which is what we want to report, as well as the cumulative percentages here.
Okay, so in SAS, we do a little bit different. So for mean, we do prop means and data equal to my data. You have to specify your data file name and just put mean standard deviation STDD EV and mean max P25, P75 stands for 25th percentile and 75th percentile. Like if you don't specify the standard deviation after the mean, it just give you the mean, no other statistics. And you put bar age and put wrong semicolon, always remember to put semicolon in SAS, and then otherwise it will give you error. So these 3 lines of code will give you the mean with standard deviation for age. And for categorical variables, we report n and percentages. In SAS, you do proc freq, also stands for frequency. So put data equal to your data name, and then put table, sex, and wrong. It will give you the n and percentages for sex. Okay, so here's our table 1. So when you compute, after you're computing those mean or percentage in your software, you want to report as this. So it just tells people your demographic characteristics. For example, in this sample, we got a mean age of 26.5 with standard deviation of 3.2. And you also have the N and percentage for sex, lifestyle. And blood pressure, remember we have both continuous and categorical. So for the continuous systolic blood pressure, we report mean with standard deviation, but we can also report blood pressure as a binary variable, like high versus normal. We have like 43.6% had high blood pressure, and 56.4% had normal blood pressure. Okay, so once you finish your table 1, the descriptive analysis, you can move to bivariate association. So the bivariate association tells us if there is a statistically significant difference between the groups in the 2 variables. For example, we want to know is the mean age statistically different between the normal blood pressure and high blood pressure group. Or we also want to know is the proportion of males and females different between the 2 groups. So for continuous variable age, we can do a t-test if it's normally distributed. And for the categorical variables, males and females, we can do a chi-square test.
Can you guys see my mouse move or no? Yes, okay, great. So for data, if you are looking at doing a t-test to compare means between 2 different groups, you use the code t-test. It's pretty intuitive. And then you're going to insert the variable name of your continuous variable that you're testing the means of. And then you're going to do a comma, and then by, and then insert the variable that you're stratifying by. So here we want to look at the difference in age by sex. So we're going to do t-test age, comma, by sex. And you can see here on the right that it gives us the mean of males and the mean of females of their ages. It gives us the difference in means, negative 0.989 here. And then that tells you that it's because it's subtracting the difference between the mean of males from the mean of females. That's why it's negative. Gives us our t-test statistic, and we're just looking at the difference between means. Are they different? So we're going to look at whether or not the difference equals to 0, and we can see here that there is a p-value of less than 0.05, so we would say that there's a significant difference in means of age between males and females. For categorical variables, we can use the chi-squared command, and this is, we're still going to use the tabulate command, which we used in our descriptive statistics, but we're going to expand on it and include both variables that we're wanting to compare, in this case, sex and race, comma, we're going to add this chi-squared command, which is chi, and then column. And this is just inserting into our cells on the right here, column percentages. You can see that 53.18% of males were white compared to 46.82% of females. You can also change this command to either be row or cell, depending on what type of percentage you want. And then you can see here at the bottom of this screen, it gives you a chi-squared test statistic of 1.39 and then a p-value of 0.706. So we would say here that there is not a significant difference between race, or there's not a significant association between race and gender in this in this sample.
Okay, so in SAS, you also use proc means as we did before for computing or compare the mean and standard deviation, but you just put a class before the var. The BP stands for blood pressure. That's a binary variable, we call it. So it will give you two means of age in the normal blood pressure group and high blood pressure group. And if you want to do a t-test, you just change the proc means to proc t-test. It's very straightforward. And for the chi-square test, you also do proc frac, but after the table statement, you put sec star BP and slash chi-square, and it will give you the chi-square statistics. Okay, so after running those codes, either in Stata or SAS, they will give you similar results. So you can start to create your table 2, which is a bivariate relationship between the blood pressure and the demographic characteristics. So we just divide the blood pressure into two groups, high versus normal. And we have the mean age in both high and normal group. As you can tell from the numbers, they're very, very similar by 0.3 years. So the p-value was not significant. It's 0.46. And similarly for sex, you can see the percentages in the two blood pressure groups of the sex groups are very, very similar. So the p-value is also greater than 0.05. But for the lifestyle, you can see in the high blood pressure group, 62% has sedentary lifestyle, but in the normal blood pressure group, 25% has sedentary lifestyle. So the difference was big. So the p-value was less than 0.01, which is significant at the 0.05 level. And then also I want to mention, like in the bivariate association, when you report those percentages, you should report column percentage. For example, here, the 62% it means like within the high blood pressure group, 62% had sedentary lifestyle and 38 had active lifestyle. So it's not very common. Like we usually don't like report row percentage in the bivariate relationship. So we don't report like among sedentary lifestyle group how many had like high blood pressure, how many had like normal blood pressure. It's always column percentage. Next slide, please.
So the third type of analysis that you can do is multivariable associations. And so first we looked at descriptive statistics, which are just one variable. Then we looked at bivariate statistics, which are two. And then multivariable analyses, we can include more than one independent variable. And the way that you can do this is with regression modeling. And so two examples of research questions that we can look at using regression modeling would be predicting the increase or decrease in, I looked this up, this is millimeters of mercury, blood pressure, which is a continuous variable. So in that case, we'd use a linear model. If you have a sedentary lifestyle after accounting for age and sex, or we can look at the same kind of relationship, but using a bivariate or binary variable of high blood pressure to predict the odds of high blood pressure given the sedentary lifestyle after accounting for age and sex. One thing that kind of happens pretty frequently in the literature is that people refer to multivariable modeling as multivariate modeling, which is not accurate. There's a difference. Multivariable modeling is what we're going to be talking about, and that's where you have more than one independent variable, in our case, lifestyle, age, and sex, but you have a single outcome of blood pressure. Multivariate modeling would be if we had more than one outcome. Say we were looking at like blood pressure and like glucose, but using the same set of independent variables. So when you read the literature or when you're doing analysis, just keep this in mind. So first we're going to talk about linear regression. A linear regression model is looking to create an understanding of a relationship between X, which would be a exposure variable, Y, which would be your outcome, and confounding variables. The typical equation for this is Y equals mx plus b. As we mentioned, a linear regression uses a continuous dependent variable, so Y here has to be a continuous variable. The constant and intercept is where Y hits on the axis when X equals 0. And then you have your slope or coefficient, which is how much your outcome changes by different levels of the independent variable. So when you interpret your beta coefficient, a value of 0 would indicate that there's not a relationship between the disease and the exposure. And if we think about this equation, that would be if beta 1 was equal to 0, our dependent variable would be equal to only the constant and intercept because X would be multiplied by 0. So a value of 0 indicates there's not a relationship between the disease and the exposure. A positive value reflects that Y increases as X increases, so your outcome increases. And a negative value reflects that your outcome decreases as X increases. And we'll do an example of this in a little bit. But I also want to talk about logistic regression, which, as we've discussed, this is when you have a binary outcome. So it's just the type of regression you use just depends on what type of outcome variable that you have. So here we have a binary outcome variable, so we're going to use logistic regression. And logistic regression looks at the relationship between a given value of X and the probability of a binary outcome of Y, and it follows a logistic function, with the outcome being a probability, so it's constrained. Similar to linear regression, a value of 0 would indicate that there's not a relationship between disease and exposure for your beta coefficients. A positive value would reflect the increase of the log odds of your outcome as X increases, and a negative value would reflect decreasing log odds of Y as X increases. And because your beta coefficient is a probability, it's more common to present it as an odds ratio or a ratio of probabilities when you're looking at like the probability of one group compared to another group. So in order to get your odds ratio from your beta coefficient, you can exponentiate your beta coefficient. And that's how it's more commonly presented. And then we're just looking at, the odds ratio associated with a 1 unit increase in X. So when you are thinking about that, think about a 1 unit increase in this number. How does it impact your Y? And this is the standard equation for logistic regression. You can see the ratio here of the probability of X over 1 minus the probability of X on the log odds scale. But the right side of our equation is the same. It's still the slope plus the beta coefficient times values of your independent variable. In Stata, in order to do a linear regression, you'll use the regress command, and that's their linear regression command. You're going to put regress, then you're going to put your outcome variable first. So in this case, we're going to use systolic blood pressure. That's our continuous version of blood pressure. We're going to put our exposure variable, which is lifestyle. We're going to put age, and we're going to put sex. Those are our 4 variables. You'll notice in front of lifestyle and in front of sex, there's this I dot. And that is because that's how we indicate this data. These are variables that are categorical rather than continuous, and it just treats them differently. So it's important to put that in front of any categorical variable. For logistic regression, we'll use the logistic command. We'll use our BP variable as our outcome. This is our binary version of blood pressure, yes or no, high blood pressure. And then our same 3 are exposure and then our 2 covariates. Another way to do this in Stata is using the logit command. However, if you do the logit command without this without this comma OR at the end, this will give it to you in beta coefficients, which is just less interpretable. So if you do logistic normally, or if you do logit comma OR, these both will give you your results in the format of odds ratios, which are just more intuitive, I think. And then there are expansions, different things you can change on these regression models, and all of those options are available in the data manuals on the software. Like how I would do that is I would just use the command help logistic, and then it'll just pull up all of the options for the logistic command.
Okay, so in SAS, if you want to do a linear regression, you just put prog_reg and data equal to my data and put all your categorical variables after the class statement. Nice thing about SAS, you can assign the reference group you want. So for lifestyle here, I put ref equal to active. So the active will be my reference group. You can also change to sedentary, just change active to sedentary in the codes. And also sex, we usually use male as a reference group. And then you put model, systolic blood pressure equal to age, lifestyle, sex, all the variables you want to control in the model. And for logistic regression, you just put prog logistic, same thing. You just put all the categorical variables after the class statement and put model BP, and you specify event equal to 1, or you can put like ref equal to 0. It will be the same. So the 1 is your outcome, your event, 0 is your reference group. And also put like the age, lifestyle, sex after the equal sign, and put run. And don't forget the semicolon.
This is an example of a outcomes table for a linear regression model, and the two columns here we have are the coefficient, or the standard deviation, and the standard deviation, and then the 95% confidence interval. We've noted the units, which is important for interpretation in a linear regression model, and then the sample size. And another important thing that's included in the table, even though it doesn't have any data, is the reference group, because that's how we're going to know who, or any reader who's just reading your table would know what this number is compared to. And we say what, variables it's also adjusted for outside of the exposure variable. So in this case, I would interpret this as those who are sedentary have 15.87 millimeters of mercury higher systolic blood pressure with a standard deviation of 2.4 compared to those who are active after adjusting for age and sex. And I would also note the confidence interval in there. This table is similar, but it's just for the results of the logistic regression model. Same thing, we have our sample size. We don't have units because we just have a binary variable of high blood pressure or not high blood pressure. Still have our reference group. Still have the other variables that we're adjusting for. And then the way that I would interpret this result is that those who are sedentary have 3.56 times the odds of high blood pressure with a 95% confidence interval of 2.34 to 4.10 compared to those who have an active lifestyle after adjusting for age and sex. And one thing that Amber pointed out that I forgot too, and so I wanted to point it out now, is that in this data, the reference group that's just standard unless you change it is the lower number. So in this case, active people would have the code of 0 and sedentary people would have the code of 1. And that's why active serves as the reference group in that. So just think about that when you are doing your stata code.
Also, does anyone know if the result is significant or not? Any idea?
Oh yeah, I was gonna bring that up too. Good point.
Yeah.
We don't have p-values in here, so
yeah. Give a try. Anyone like who may any idea like if it's significant or not?
I would
No
say
one.
yes,
You would
Yeah,
say
why?
why?
because of the odds ratio, it's higher than 1.
Close, close, very close. Good try. But the answer is yes. But any other thoughts?
Think about the confidence interval.
Oh, I think I got it because of the odds ratio. It's in between the confidence interval. No?
I don't think we covered this. I feel bad. Okay, yeah, we didn't talk about that, but like very close. You are on the right track.
Yeah, we did
So
not tell you the answer to this.
yeah, so for like odds ratio, we compare with 1. So if the confidence interval contains 1, it means not significant. If it does not contain 1, for example, this is from 2 to 10, it does not contain 1, it's significant because for odds ratio, our reference group is 1. So the comparison group, the odds of having the outcome is 1. But our center lifestyle group, the odds is 3 times. So I'm saying we're getting close, but because we're just comparing the confidence interval with 1. But if you're doing like linear regression, we compare with 0. Odds ratio, you will think is a comparison. Like the long value will be like 1 divided by 1 will be 1. But for like 0, like linear regression, it's 1 minus 1. It's 0.
Yeah, I think that too. Like, say your confidence interval. You say that this value, the odds ratio, is still 3.6, but your confidence interval was like 0.8 to 4.10. There's a good probability that, not like a good probability, but there's still a large enough chance that since our confidence interval contains negative numbers, there's more, variability in there, and we're not confident enough to say, that that's significant. So the fact that the magnitude here too is also like 3.56, and then the magnitudes or the lower end of the confidence interval starts at 2.34. It would still technically be significant if the confidence interval started at like 1.01, but this is pretty far, away from 1. So that's something that you want to keep in mind too. All right.
Any
questions?
I do have several questions. Well, first of all, I wanted to know what kurtosis is because I had never heard of it in any of my stats courses.
I'm just trying to go back to here. I think this is where I just mentioned kurtosis. Amber, do you want to do it or do you want me to do it? Are you frozen?
Go ahead, if you don't mind.
Okay. Kurtosis and variance and skewness are just things that you want to look at when you're looking at the different assumptions of your variable. So we didn't talk about it in this PowerPoint, but it would take, like a full course or a full, at least, a couple of courses to talk about different assumptions that you need to meet when you're doing a regression model. But there's different, for linear regression, if you're using a continuous variable, like there's assumptions of normality and there's assumptions of constant variance and a few different things. And these are just different tools that you can use to help determine whether or not those assumptions are met. Does that help?
Yes.
Okay.
And then just a second question that I have is, I've used R before, and I know that one gives you can get graphs and charts from it. And I just wanted to know if Stata or Stata and SAS also have something like that.
Yes, that's a very, very good question. So R is very user friendly in terms of creating figures and charts, and they have different packages and they create just beautiful figures. But in SAS or Stata, in my opinion, it's not like that user friendly because they do not have that many packages just for like charting, like creating graphs and figures, but you can still make graphs. So for SAS, you just do like plots. There's a command. If you're interested, like I can send you links. But in my opinion, R is way easier in terms of like making figures and charts. I usually like when I have to make something, I go to R's. Like I don't, I rarely like make my figures in SAS. It's just not that easy.
I do a lot of figures in Stata, but I think that, you know, R and Python and all of those more data sciencey options have just like more options, and they often look just prettier. So, you know, I like it that way too.
Thank you.
I guess too, sorry, one more thing. Variance and skewness and kurtosis, they're just like, oh gosh, I wish I had a data set up to just show you. It's just, they're just ways to explore your data and kind of see how your variables are, like skewness, like are your continuous variables following along the bell-shaped curve. That's how it's gonna, it just gives you some information on that. Is it like normally distributed, all of those things. So. I'm gonna stop the slideshow.
Okay, all right. If no other questions from the students, we can have a 20 minutes back. And feel free to email both Noreen and I if you have any like further questions. I think we're going to upload this video in YouTube, and then they're going to send you a link. And then if you need the slides, let me know too. We can share with you. All right. Thank you, guys. Have a good weekend.
Thank
Thanks,
you.
everybody.
Thank you.
Bye.